Okay, I want you to picture something. Imagine simulating an object that has a trillion moving parts. I mean, that's more complex than any machine humans have ever built. Now imagine doing all of that on your laptop. Yeah, sounds like total science fiction, right? Well, in this explainer, we're going to break down exactly how this is actually starting to become a reality.
So let's just dive right in with the big question. Can you really do this? Can you simulate a chip with a trillion transistors right there on your laptop? I mean, on the surface, it sounds completely nuts, impossible even. But we're about to walk through the incredible techniques that are making it happen.
All right, first things first, we really need to get our heads around the scale of this thing. This isn't just another small step in computing. No, this is a colossal leap. So let's frame the challenge. Let's talk about the trillion-transistor problem.
Just take a second and look at that number, 1 trillion. That's a million millions. It's one of those numbers that's so ridiculously big, our brains just kind of short-circuit trying to grasp it. Now try to imagine modeling the behavior of every single one of those components, all at the same time. Yeah.
So what really makes this so incredibly hard? Well, for just one tick of that chip's internal clock, the sheer amount of data that a trillion transistors would spit out would bring most supercomputers to their knees. And that's before you even start thinking about modeling weird quantum effects or the tiny, inevitable manufacturing flaws. The whole thing becomes a true computational Everest. Which, of course, leads to the most logical question of all. If this is so insanely difficult, and we can't even build a physical chip this big yet, why in the world would we even try? What's the point? Here's why. The prize at the end of all this is absolutely world-changing. A chip with this kind of muscle could unlock genuinely intelligent AI. It could completely revolutionize medicine by letting us design personalized drugs at a molecular level. And it would let us model things we can only dream of right now, from our planet's climate to the inner workings of stars. Okay, so the problem is massive, but the reward is, huge. So how do we possibly bridge that enormous gap with the machines sitting right on your desk? Well, it all comes down to using a really smart strategy. The whole philosophy here is actually pretty simple. This isn't a brute force problem. You can't just turn a laptop into a supercomputer. That's impossible. The big breakthrough comes from a total shift in thinking. It's all about being clever, being efficient. It's about working smarter, not harder. And the number one key to working smarter is this idea called abstraction. So instead of trying to simulate every single one of those trillion transistors one by one, you simulate the important functional blocks. Think of it this way. If you want to understand traffic in a city, you don't need to model every single piston firing in every car engine, right? You just model the cars. It's the exact same idea, just on a microchip.
The next trick is a process called progressive refinement. So first, the laptop runs a super fast, kind of blurry, low-detail simulation of the entire chip. This just gives it a rough sketch of what's going on. Then, it intelligently pinpoints the hotspots, the really critical areas that need a closer look, and only then does it pour its resources into simulating just those sections in super high detail. It's like using a surgical scalpel instead of a computational sledgehammer.
And this completely changes what your laptop is actually doing. It stops being the only engine trying to do all the heavy lifting by itself. Instead, it becomes the smart conductor of a much bigger orchestra. It's just directing traffic and telling everyone else what to do.
So what's in this orchestra? Well, your laptop can send the really intense calculations off to the cloud. It can use specialized external hardware, like FPGAs, which are basically these cool, reconfigurable chips made for specific jobs. And right there on board, it uses clever memory tricks and custom software to squeeze every single drop of performance out of its own hardware. But look, clever strategies and fancy hardware, that's only half the story. The real magic, the secret sauce, happens at the deepest level, in the code itself. This is where we see some truly ingenious algorithms. To get the difference, think about this. The old brute force way is like a security guard who watches every single empty room in a giant building all night long. It's a huge waste of energy. But event-driven simulation? That's a guard who only pays attention when a door actually opens. It simulates only the parts of the chip that are actually doing something, which cuts the workload down exponentially. And believe it or not, it gets even smarter. We're talking about using machine learning to predict what a circuit is going to do, so the simulation can just skip calculations it doesn't need. Advanced math to lighten the load on the memory. It all comes together with this intelligent scheduling that makes sure every part of your laptop's brain is working on the most important thing at exactly the right moment. So, when you combine all of these smart strategies with these incredible breakthrough algorithms, something really amazing starts to happen. We're not just talking about a neat tech demo anymore. We are looking at the dawn of a whole new computational age.
What you get at the end of the day is the rise of what you could call the desktop supercomputer. The power to solve problems that used to belong only to massive government-funded labs is now moving into the hands of regular researchers, engineers, and, well, anyone with a great idea.
So what does that actually look like? Well, imagine personalized drug discovery. A doctor could sequence your unique DNA, and then, right there on their desktop, simulate millions of different drugs to find the one that is perfectly tailored to your body for maximum effect with minimum side effects.
Or think about AI. I'm not talking about the generic assistants we have today. I mean a truly personal digital companion that runs right on your device, learning and adapting to you in real time, with a deep understanding of your world and what you need.
And maybe the most important thing of all, this leads to the democratization of science. When this kind of computational power isn't locked away in huge institutions anymore, it unleashes a wave of innovation from everywhere. The next giant breakthrough could come from a student in their dorm room or an inventor in their garage.
So we've seen how clever thinking, smart algorithms, and just being a good conductor can make the impossible possible. By working smarter, not harder, the power of a supercomputer is moving to the desktop. And that brings us to the real question here. If this power was in your hand, right now, what groundbreaking problem would you solve?